So my recording stopped in the middle, so I have to continue from where I left. I hope it is recorded, the previous one. So where do I check it? Just a minute. Okay, everything is good. Yeah, we were talking about the limit, right? So what should be the limit every time I do a shifting of n plus k? So every time you do a shifting of n plus k, whatever limit you have to go k back here, because that is what I think. Like for example, so for example, let's say I have x power 3, and this summation, I mean, let's say I have x1, x2, x3, and so on. And okay, no, let me just write like this. One is missing, right? X square, x cube, and x4, and so on. So let's say my summation was starting from 2, right? My summation is starting from 2 here, and I want to make it start from, let's say, no, I want, like, this is x square, right? My summation is starting from 2. If I want this to be 0, like in the standard form n equals to 0, so what I can do is I can go to back here. No, I don't need to go to back here. Wait. Yeah, I can go to back here everywhere. I will just go to back everywhere. And what I will do is, so this will be 0, this will be 1, this will be uh, 2, and I will write this in the form of summation. Now I have that form, x power n. But now what I can do is, I went to back, right? Now just add the 2 back. So basically, subtract 2, add 2, subtract 2, add 2, subtract 2, add 2. This is one of my professors told that one of the strongest tools in mathematics is by adding 0. I didn't know what he told at that time, but now I understand. uh, so these terms are just your indices. So this is the similar thing I did here actually. So you remember this, right? So if this is the case, there was a 2 here. I wanted 0 to be here, not 2. Well, 0 is here overall. I can just add 2 and subtract 2, right? Now this will become 0. Oh, no, wait, I want this dependence. uh, this will become 0 because this thing by default starts with 2, right? So now you have 0, 1, 2, 3, and so on, and this is 0. Okay, I don't think I need to talk much about it. Like, while you are solving a problem, while you are analyzing whatever question you have, you will figure out eventually. Like, I don't need to. Yeah, it is a good. I think it is interesting. Like, but why am I? I don't know. I like making things complicated unnecessarily. So let me just. So finally, I can take x power n common. Oh yeah. Also, yeah. This should be cn. Cn will be here. And cn, wait, cn will be here. Let's see, will cn be here? Cn, oh, I shifted n by n plus 2 everywhere, right? So there will be cn plus 2 here, multiplied by cn plus 2. Now I have n plus 1, n plus 2, c of n plus 2, omega square. No, not omega square. Should I have omega square? No, I think omega square. Let me just write cn. Okay, this looks correct enough, right? This should be correct. Now the idea is, so doesn't matter whatever x is. If I'm always getting 0 here, this means all of these should be 0. That's math for you. That's a belief. That's what all the cracking of the head for our says. So we have this, and also by the way, I can also change the index with for k. I will just use k now because that is what textbook uses, so that I can compare it with the book. So if I do that, k is my just my dummy index. So here we go. So here we go. So here it is. So now I have a relationship between the coefficients. So if I know C1, I will generate all the other coefficients. I mean, if I know C0, I will generate all the other coefficients C0. I mean C2, C3, C4, C5. I mean, not C4, like all the two steps getting added every time. So C4, C6, C8, and so on. And if I know C1, I can generate all the odd terms. That's a basic pattern. I don't know, like this is so much complicated things, but somehow it boils down to patterns which even a child can understand. Uh, so these two will be my completely independent coefficient, which won't have any idea of. So let me analyze one by one. Suppose I want to find. Suppose I know C naught, then my C1 will be. I mean C2 will be 2 times C0, right? And then my C4 will be C2, what will it be? It will be minus omega square uh, by k plus 1. I mean, so yeah, here will be C2, 2 plus 1, 2 plus 2, 2 plus 1, that is 3, and times 4. But I know the value of this coefficient as well, which will be equal to minus of uh, omega square times omega by 3 by 3 times 4, and this will be omega square by minus here as well, 2 and times C0. So C4 can be written as omega square whole square C0 by 2 factorial. Actually, for any even uh, if you keep doing this, somehow you will find that this is the relationship. You can verify it yourself. uh, I might be wrong as well, but I think this is all there will be. So uh, will it be the case when second coefficient, third coefficient, fourth coefficient, fifth coefficient? Yeah, I guess I want to make it more generalized. Like, how can I do that? So, so let me try it. So, any ck plus 2 can be written as some function of k times ck, right? So, if I use induction, I don't know what I'm saying. So this means initially this will be the case. And so then what I can do is C4. I can immediately say what C4 should be. This will be, and this will be, so I can do a conclusion that for the even numbers, like the nth even coefficient will be actually product of all the, how should I say, should I write k plus 1 or k minus 1? I think it would be better to write 2k minus 1 uh, from 0 to infinity, 0 to your n, right? So I guess this is how it is supposed to be happening. uh, oh no, okay, okay, wait, not 2k minus 1, it is just 2k, sorry, 2k, I messed up. 2k, so until there I have to go. And if I do this, what would I observe is, let us see how would it look like. So it will be pi k equals to 0 to n. So I know for general how the k would look like. So it will be so f of k is minus omega square k plus 1 k plus 2. So this means that f of 2k is minus omega square by 2k plus 1 2k plus 2. This is how it would look like. So if that is the case, let me just substitute it, minus omega square divided by 2k plus 1 2k plus 2 C0. And if I do more math, then I think I should be able to tell what this would be as well. So I think I'm pretty sure there must be some relationship for factorials as well. Like for example, I can write n factorial as what happened to this? Okay, some pen issue. N factorial as okay, one as something like this. Oh, I have to strictly start from 1 in this case, right? This is a classic example. And also the thing is, if I do something like this, this is also a valid example, but the thing is, every time what will happen is it will be something like this, right? So this will be my first generation, then my next generation will be so it would be 2 times 3, and then it will be 3 times 4, and so on. So this will be the first term, second term, third term, and you can see that basically all terms are getting multiplied twice. This can be ignored, and so this will be like again up to n. If I go, it will be n factorial square somewhat, right? uh, by the last term, because the last term will be left out a little. So I don't know what would I do with this, but this is somewhat similar to that. Like if I analyze this, this will be something like so we are starting from 0, so the first term will be 1 times 2, the next term will be 5 times 6. Okay, this is very weird. I didn't mess up somewhere. I didn't mess up somewhere, honestly. Hmm. Okay, I am overthinking. So I have to start from 0, right? When I do 0, it will be 1 times 2. So when I substitute 1 now, it will be 3 times 4. Then it will be, when I substitute 2, it will be, no, I have to substitute 3 now. Uh, what am I doing? This is for 0. Okay, my pen is not working, and that's making me a little anxious. Now if I substitute 2, it will be 5 times 4, 5 times 6, and so on. So you can see this is like 2n factorial, right? This is only found out after you check, or else it will be very difficult. I think it is just hard to tell. I can't just look and tell. Apparently that is what I feel. I wish I can, but no, there is no way of telling apart. uh, hmm. So maybe I can think it like this. So 1 2 is there, right? So it's like 1 2. Every time there is 1 2 1 2 1 2, and uh, so you're just getting numbers jumped by 2 steps for with products every time. So here it will be as it is, but here what will happen is you will just jump 2 steps, and this will be uh, so from here. Okay. And somehow every time you are jumping 2 steps, you are having a continuity, like 1 2 3 4 5 6, right? So okay, whatever it is. So okay, apparently, so I can write my coefficient as minus 1 power n, the even coefficient, of course, minus 1 power n times omega square power n, and 2n factorial, where n can be, yeah, of course, c naught is there. N is an integer, 0 1 2. And if I do the same thing for the odd one, let me do it. I don't want to just, I know the result, but I will just do it and see. So I know that ck of plus 1 for the other case. Okay, but tablet is not working. I will use my fingers to write today. So ck plus 1, I mean 2. Ck plus 2 is, as we know, is again the same thing, the same concept, k plus 1. But the thing is, now we are dealing with odd numbers, c k. So uh, again, if I do everything, uh, let me not do everything. So I know that c3 will be this. So it will be what will this be? 2 times 3, c1, c4, no, not c4, now it is c5. This will be uh, minus omega squared, uh, 3 times 4, and then will it be 3 times 4, k plus 2, no, it will be 4 times 5, 4 times 5, and times again this minus omega square 2 times 3, and so on. And again, if I follow this pattern which I am seeing apparently, so for any odd number, let me use this now. I will have again minus 1 power n omega square power n divided by 2n plus 1 factorial uh, c1. So my general solution will be a linear combination of these independent coefficients c1 times, I mean, some function multiplied by this independent coefficient c1, c0 and c1 can be anything. They have no boundaries, any real number you can imagine. In fact, I think any complex number you can imagine, they can be anything, it doesn't matter, they are just constant numbers, right? So, and yeah, let us say that just index is from summed over some 0 to infinity in both cases. Okay, let me just write it down, and this will be did I miss anything again? I don't think I missed anything this time. uh, oh yeah, of course, how can I forget the coefficients themselves? So here all the even coefficients will be there, which we saw, and here all the odd coefficients will be. Yeah, so now it's perfect. Now and so and what should I say more, like omega is just a constant number, and I can just multiply omega by omega here and nothing will change, there will be still a constant. uh, so this is nothing but I think cos of omega x, and this thing is just a sine of omega x, and that's it. This thing will just get inside this, I mean, it is just some constant which can be anything. It's like a black hole, so I will just sink this inside this, and yeah, that's right, I guess. Theory, let's see theory. Hmm. What more is he doing? Hmm. Hmm. Okay. 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 Hmm. Let's see. Hmm. Hmm. Okay. Hmm. So we have this relationship which we actually did ourselves, and yeah, it is just talks here and there. But the X power k thing was, I think, important. In clinical equation, I don't know what it is. Let us try solving something more. Hmm. So, hmm. Okay, he's like just symmetries, huh? Okay, suppose I found a solution which is even from an homogeneous differential equation and also an odd. So I got two of these. But what is this? Is there any? Is it that I have to always get this? Is there something necessity like this? What is this? Okay, this is new for me. Okay, for what exactly? What is there about symmetry here exactly? Mm, so if I have this form for the differential equation, uh, what would happen if I apply this on x for a function f of x? Uh, Nothing special would happen, right? Like I'm just applying this on x, a linear function. Uh, so what is so nice about this? Hmm. Okay, maybe some other time this one. Okay, so this is the Bessel's equation. They do a similar thing to solve this one as well. Hmm. They assume they have some solution form and they just substitute it in the differential equation, and let's say lambda is 0, you get this, you have the possible k values, k is plus or minus n. Hmm. Hmm. Okay. Mm-hmm. Okay. Hmm. Okay, he got a solution. Fine. We got something like this. What is so special? I don't know. Hmm. Okay. So this is the Bessel function apparently. I am being lazy. I want to derive this. Maybe someday I will derive uh, this. Now singularities. So what is the theorem? I don't know. Hmm. All these various problems which I really don't want to solve at this point. Maybe some other day. One more thing I want to talk here is suppose you have a second order differential equation. Let me write that down neatly. Homogeneous differential equation. And suppose you know two of its solution. You found the solutions. So these are two linearly independent solutions of this differential equation. Now the thing is, if these two are linearly independent, we know that the Wronskian of this will be non-zero. If two functions are linearly independent, then their Wronskian should be non-zero. Uh, Someday I will also talk about Wronskian, but not now. Just for now, it is like if it's if the Wronskian is non-zero, then my two functions are linearly independent. That is all I can do right now. Now, if I differentiate this, what I would get is, so let me just write y1 y2 prime plus y1 y2 double prime, and I have minus y2 prime y1 prime minus y2 y1 double prime, and what makes this is this. And finally what happens is I get y1 y2 double prime minus y2 y1 double prime, and I can substitute further because I know y2 double prime's value because of my general form of differential equation. It is minus p uh, y2 prime minus q y. Similarly, I can write minus p y1 double prime minus q y1, and these two will just cancel each other out because y1 y2 q y1 y2 q. So the remaining part will be this apparently, p of x times minus p of x times y1 times x y1 y2 prime Is it correct? Yeah, minus y2 y1 prime double prime y1 prime. Yeah, there is no double prime. And basically, my derivative of the Wronskian will be equal to my function, which is the coefficient of x times uh, my Wronskian itself. So you can see, like, I got a relationship between the Wronskian and the coefficient of first derivative in my differential equation without even without involving any uh, solutions. Like this equation doesn't have any of the solution. So this means even if I don't know the solution of the differential equation, I can still find out the Wronskian. That's crazy. So this means that dw by w is minus p of x, and this means if I have some reference function, then this implies that this should be equal to minus some reference function times xp of x. X prime is just a dummy variable, I want to integrate it, right? So yeah, also this is w. This means that my Wronskian, I can calculate my Wronskian just by knowing my how should I say, uh, coefficient. I don't need to find the differential equation. And the even crazy fact is, suppose I know one of the solutions y1 and I want to find what is y2. Suppose I know y1 and I want to find what is y2. I can do that using this relationship now, because I know that my Wronskian is equal to y1 y2 prime minus y1 prime y2, and so what more can I do? This is equivalent of writing y1 square times y1 y2 prime minus y1 prime y2 by y1 square. So this means that uh, yeah, so w of x can be written as y1 square times the derivative of y1 by y2, or is it y2 by only 1 minute? What is derivative of f by g? That's f g prime minus gf prime by g square, right? Yes, it is. Okay, so I have to include a minus sign here, no problem. Y2 by y1, this will be y2 by y1 whole square. So this means this will be w of x by y1 whole square, which will be, as we have seen, the exponential of a to x uh, p of x dx divided by y1 square, and it might get even uglier. And so this is equal to d by dx of, oh, there is no whole square anymore, I just differentiated, so y2 by y1. This just means that if I know one of the solutions, I can easily find the other solution by integrating this term. I know which is a mess in itself, but technically, if we can do it, we can do it. So, exponential of uh, some initial constant times p of x dx by y1 square dx. I hope I did it right. I almost did it right. This will get multiplied with y1 of x, and minus plus doesn't matter if if f of x is the solution, f of minus x is also the solution. So I will just write integration with some initial value which I know. Uh, yeah, y1 integration exponential, yeah, minus should be inside here, minus x p of x dx by y1 square. So this is the form. If you know one linearly independent solution, you can directly generate the other linearly independent solution with this equation. And one special case, if there is no coefficient of the first derivative, you can just also let me write x prime just to uh, mention it is a dummy variable. So x prime, then x double prime, x double prime. Yeah, now we are good. And now because these two are dummy variables, they will just get integrated up just to get finally the x which is in the left side. And yeah, he gave an example which if you know sin x as one of the solution, you can generate cos x as the other solution, which is amazing. Hmm. Hmm. Okay, this is out of my head. That's all for now, I guess. I also wanted to talk about Sturm-Liouville form. Uh, so basically, the Sturm-Liouville form is okay. I think some other day I will talk about it. Bye bye.